Welcome to our video on the next part of calculus, which is all about integration. In this video, we will discuss antiderivatives and indefinite integration. Now, our warm-up says that if we have some f prime, some derivative of f, and it equals 3x squared, we want to figure out what could have f of x equaled. Go ahead and pause the video and see if you can figure this out. Any ideas? Well, basically, we want to figure out what f of x was so that when we took the derivative, we got 3x squared. Well, that means that our f of x, our original function, would have had to have been x cubed. Because when we use the power rule and take the derivative of x cubed, the 3 comes out front and we move down to squared. Now, what if f of x had something else on it? Like, what if f of x was x cubed, but then plus 8? If we took the derivative of x cubed plus 8, we would still get 3x squared. This plus 8 goes away when we find the derivative. There are actually an infinite amount of possible f of x's, or possible functions, that have the derivative 3x squared, because that constant could be anything. We call these f of x functions here the antiderivatives of 3x squared. There are an infinite amount of them. In this video, we will learn about what antiderivatives are. Well, you kind of just saw it. But we'll learn about what they are using proper math notation, and then we'll talk about what indefinite integration means. In calculus, a lot of times we have capital F, and then we have lowercase f as well. This is just calculus notation, and it's a way that we define and use antiderivatives. So we have a function capital F is an antiderivative of f, lowercase f, when we take the derivative of capital F and get lowercase f. It's confusing to say out loud because there's really no better way to say it. However, the idea is that when you take the derivative of capital F, you get lowercase f. That means when you go backwards and you find the antiderivative, that's capital F. Let's take a look at this example again that we had in our warm-up. We have lowercase f, our function, is 3x squared. We want to take the antiderivative of that and find possible capital F of x's. We already did this, and we said that one possibility for the antiderivative of 3x squared was just plain x cubed. Another possibility, which I'll call f sub 2, was x cubed plus 8. A third possibility could be x cubed minus 5.4, right? Because all of these have the same derivative of 3x squared. Now, there's an infinite amount of them. We could keep going. But in general, what we would say is that big F of x, the antiderivative, would be x cubed plus c, where c is catching all of those possible constants that we could have added or subtracted from the x cubed part. If we take the derivative of x cubed plus c, we always get 3x squared. So c stands for the constant that we have to make sure we include, because again, we could have had any constant here, and then we take the derivative, get 3x squared, and that constant would have gone away. So we have to take into account that there is a possible constant, even if it's 0. Another big idea in calculus is differential equations. And in college, if you go high up into mathematics or engineering, you will take an entire class called Diff-EQ, differential equations. We've already dealt with a derivative of 3x squared. We've dealt with that in a couple examples so far in this video. And that is the equation of a derivative. That's all a differential equation is basically the equation of a derivative. Your book defines it as an equation that involves x and y. I put any variables because they might not always be x and y, but they usually are. And then the derivatives of y. In this chapter, we're not going to delve too far into differential equations, but we'll get there later. Let's take a look at an example of a differential equation. G prime of x equals 2x. This is a differential equation, diff-EQ, because it is the equation of a derivative. Let's think about what the general solution to this differential equation is, meaning find the original function, g of x, such that its first derivative, g prime, was 2x. Well, what did we take the derivative of to get 2x? We took the derivative of x squared. Because when we take the derivative of x squared, we get 2x. Now, just like in our previous example, what if there was some constant after this that went away when we found the first derivative? We have a sort of catch-all constant of plus c to take into account for whatever constant that could have been there. This is called the general solution of our differential equation. It's a general solution because we don't know the exact function g of x that we're talking about. All we know is there's a family of solutions or functions that it could have been. So the best that we can do so far is the general solution of g prime of x equals 2x is g of x equals x squared plus c. Let's find the general solution for each one of these differential equations. In number 1, we have a pretty simple one, y prime equals 3. We want to know what the general solution is, so that would be y. And what did we take the derivative of to get 3? Well, we took the derivative of 3x. Now actually here, I don't even know that our other variable is x. This is not denoted dy dx. It's just y prime. So you could have easily put 3a, 3p, but I'm going to use x because that's what we normally use. And then we, of course, have to take into account that there could have been a constant there. So the general solution of this differential equation, y prime equals 3, is y equals 3x plus c. In number 2, our differential equation is f prime of x equals x squared plus 3. This one is a little bit more difficult to work backwards from. We have two terms here, but the first one might be a little bit harder to think about. Can you think of what we had to take the derivative of to get x squared? Well, we know there definitely had to have been an x cubed because we used the power rule. Now, if we think about using the power rule on x cubed, there would have been a 3 out in front, and it would have been 3x squared. But we don't have a 3 here. We have a 1. So when we took this 3 out front and used the power rule to find the derivative, that 3 had to multiply by something out front to cancel out and leave us with just a 1 out in front. So we had to actually have a 1/3 out in front here. Let's check by taking the derivative of 1/3 x cubed. When we take the derivative of this using the power rule, the 3 times the 1/3 cancels to 1, and then we do x squared. So this works. The next term we want to antiderive or integrate is 3. We already did that over here. The antiderivative of 3 is 3x. Then we of course need to account for that potential constant at the end plus c. So our general solution to f prime up here is 1/3 x cubed plus 3x plus c. And if you need to check your work, you of course have a built-in check system, and you can just take the derivative of this and see if it's f prime. We already checked here, and we checked this one in number 1. Here we're going to delve into some notation for these antiderivatives we've been studying so far. Now what I recommend is just watching this first part and seeing it play out, and then I will star the stuff that you should definitely write down in your notes. Let's start off with this differential equation, dy dx equals f of x. To make it a little simpler, let's multiply both sides by dx, so we'll have dy equals f of x dx. Then what I'm going to do is introduce a new symbol. In order to find the general equation, I am going to take the integral of both sides. The integral is this snake-like looking symbol that will be in pink. Now, the integral of just 1 dy is just y. Over here, we still have our integral of f of x dx. Now, this is called an indefinite integral because, as we'll see later, there could be numbers here, and here. And since there are no numbers here on the integral symbol, it's called an indefinite integral. Once we see numbers there, that'll be a definite integral. But as for right now, this is saying what is the antiderivative of the function f of x with respect to x. So as we've already defined, the antiderivative of this is capital F of x, and then of course plus c to account for the potential constants on that antiderivative. Here's what you should write down in your notes. This line right here, and then I'm going to point out all the vocab associated with this. As mentioned previously, this little snake-like S symbol is called the integration symbol, and it's telling us that we're about to take the integral of something, aka take the antiderivative of it. F of x, the function on the inside of the integral, is called the integrand. It's what we are integrating, or taking the antiderivative of. The dx after the integrand is called our variable of integration. It's telling us that we're integrating with respect to the variable x here. This very well could be dt, dA. It just has to match the variable of our function. In this case, it's x. We've already discussed that capital F of x is our antiderivative. It's basically our answer, but this plus c, we already know stands for a constant, and it's called the constant of integration. Anytime we are asked to find a general solution, we need that plus c constant of integration. Here are some snips from your book. The top one is basically what we just saw, but instead of capital F prime, we use lowercase f. They mean the same thing. When we're taking the integral, we end up getting the antiderivative capital F of x plus c. And then this one looks a little bit more confusing, but basically all we're saying here is that taking the derivative and the integral of a function kind of cancel each other out. Differentiation and integration are inverses of one another. They kind of undo each other. Then we have some basic integration rules. Just like we had basic derivative rules and we had an entire PDF dedicated to them, we have the same types of rules with integration. Now, I do not recommend writing every single one of these down in your notes. Instead, you will have a PDF that you can download and use, but I want to show you just a couple. So if we see the biggest one here, which is the kind of the backwards power rule. So we obviously know our power rule. If we take the derivative of x to the n, we bring the n out front, and x gets raised to the n minus 1. Then going backwards here, if we're taking the integral of x to the n, what we instead do to go backwards is instead of taking 1 away, we add 1, so it's now x to the n plus 1, and then we divide by that n plus 1. So this is probably one of the most important ones that we will be utilizing. This, of course, does not work when n is negative 1, because that has to do with natural log, which we'll get to in the next chapter. Let's put these basic integration rules to the test with some basic examples. In number 1, we want to take the integral of 3x dx. That means we want to find the function such that when we took its derivative, we'll get 3x. I took a little snip from the basic integration rules, and this is the power rule but going backwards. I say it's the power rule going backwards because the power rule is telling us how to take the derivative of x to the n. Sort of backwards, or the inverse of it, is taking the integral of x to the n. Now we have 3x to the first here. So in this case, our n value is 1. The 3 can just stay here, or we can take the 3 out front. Either way, let's not think about the 3 too much. We're really taking the integral of x to the first. So this is telling us that it becomes x to the n plus 1. Well, in this case, since n is 1, it's going to be 3 to the 1 plus 1, or 3 squared. Then, in our denominator, we'll have n plus 1 as well. So whatever was up here ends up being what we're dividing by. That is a 2. So I'm going to put the 2 out front. Now let's make sure this works, meaning we want to take the derivative of this quickly and make sure we get 3x. If we bring the 2 here, it cancels with the 2, and we have 3x when we take the derivative. We, of course, need a plus c, and that is our general antiderivative, aka the integral of 3x dx. In number 2, this is also going to be a backwards or integrating with power rule. Let's rewrite this as the integral of x to the negative fourth. So once again, we're using this backwards power rule to integrate, figuring out what did we have here such that when we took the derivative, we got x to the negative fourth. Well, it looks like x to the n dx, and of course n is not negative 1. Our n here is negative 4. So we're going to add 1, and that becomes our new exponent. Now be careful when you add 1, just because it is a negative. So we'll have x to the negative third when we add 1. That is also what we're dividing by. Then of course we need a plus c. Now I want to rewrite this in a nicer way. So this is negative 1/3, and then the x cubed is in the denominator plus c. For number 3, we can again rewrite to make this a little bit simpler. So the square root of x is really x to the 1/2. So once again, we can use this backwards power rule, or the power rule for integration. Our n here, our exponent, is 1/2. So we're going to add 1 to that and get 3/2. So we'll have x to the 3/2, and then we of course want to divide by that value of 3/2. Dividing by 3/2 is the same thing as multiplying by 2/3. And then of course we need our plus c, our constant of integration. Now I didn't discuss this for number 2, but for all of our solutions we can of course check our work by taking the derivative. If we took the derivative of this term here, using the power rule for derivatives, bring the 3/2 down front, multiply by the 2/3, reciprocals cancel, and take 1 away, which is 1/2. So we'd have x to the 1/2, which is the square root of x. The derivative of a constant c is nothing. So the derivative of this would be what we want, the square root of x. In number 4, we have the integral of 2 sine x dx. What we can actually do is bring that 2, that constant, out front to make this a little simpler. So it's 2 times the integral of sine x dx. This is our rule, and if you think about it, this is not something that you need to memorize, but rather just think of it as the backwards form or the inverse form of the derivative. If we took the derivative of negative cosine, we of course would get sine. So, using this rule, the 2 remains out front. The integral of sine of x dx, basically what did we take the derivative of to get sine of x, is the opposite of cosine. So we have negative cosine x plus c. I'm just replacing it. This, of course, is negative 2 cosine x. Now, we do not need to multiply by plus 2c. Since c is just a general constant, 2c is also just a general constant. So in general, all we need to ever write is just plus c to account for whatever constant that is. Let's check our work real quick by taking the derivative just mentally of this. We should get 2 sine of x. If we do that, the derivative of negative 2 cosine x is positive 2 sine of x. Because the derivative of cosine is negative sine, the derivative of negative cosine is positive sine. And of course, the 2 out front doesn't really do too much. The derivative of this constant c is, of course, 0. In number 5, we're taking the integral of a polynomial function, a trinomial specifically, and if you'd like, you can actually rewrite this as the integral of each term to think of it separately. Now I'm writing it out like this because sometimes students like to see that you can take just the integral separately of each term as long as they're separated by plus or minus, similarly to how we had the sum and difference rules for differentiation, where you took the derivative of each term that was separated by a plus or minus. We can do the same thing with an integral. So I'm going to write it out this way for this example. Note that I won't always do it this way, but I just want to show you we can think of it as 3 separate integrals because they're separated with plus or minus signs. Using that backwards power rule for all of these really, we see that we have 3x to the 4th. So this 3 will just keep out front. And then using the backwards power rule or the power rule for integration, we're going to add 1 to this 4, and that is both what x gets raised to and what we divide by. If you do a quick derivative check here to make sure that you get 3x to the 4th, you'll see that it works. Using the power rule for differentiation, the 5 gets brought out front and cancels with this divided by 5, leaving us with 3x to the 4th. In our next term, we're going to do the similar thing. Minus, the 5 stays. It ends up being x to the 3rd, and we divide by that 3. Then in the final term, we'll have an x squared, and we'll divide by a 2. Then, of course, we need a plus c at the end. Number 6 looks a bit more complex, but check out that we only have one term in the denominator, and when you have that common denominator, we can actually separate this and rewrite it so it's a little bit simpler. Rewriting it with both of these terms from the numerator over their common denominator makes it a little bit simpler. And then once again, we see that we can simplify here. So we have x to the first over x to the 1/2. When we're dividing powers with the same base, x, we subtract. So 1 minus half is half. So our first term ends up becoming just the square root of x, or x to the 1/2. Then our next term I'll rewrite as a power as well. It's 1 over the square root of x, so it's really x to the negative 1/2. So now we have a much simpler integral that we can just use that same power rule for integration on both of these terms. Using the power rule for integration on our first term, we want to add 1 to our 1/2, and we'll get 3/2, and then that is the same thing we divide by. Now dividing by 3/2 means multiplying by 2/3, so the 2/3 goes out front. Then in our second one, we have x to the negative 1/2. So once again, we're going to add 1, and when we add 1, we'll get x to the positive 1/2, and we're also dividing by that positive 1/2. Dividing by a 1/2, again, means multiplying by its reciprocal, which is 2, and then we, of course, have a plus c. In order to check your work, you can take the derivative of this final answer and make sure that you do, in fact, get this, which simplified back to here, which simplified back to here. So a lot of times when you see a quotient, what you can do is if they have a common denominator, you can rewrite. Once you rewrite, you kind of break down each term and see that they really are simple power rule integration. In problem 7, we again have a quotient, and this one is a little bit of trig, which we haven't done too much of yet. So when we rewrite this, we see that we have a cosine squared, so we have sine of x over cosine of x times 1 over cosine of x. I rewrote it in this way because this cosine squared is really cosine times cosine. Sine is really just sine times 1. Of course, we still need the dx there, our variable of integration. Now, sine and cosine are the building blocks of trig, so we can rewrite sine over cosine as what it really equals, which is tangent. Then 1 over cosine, or the reciprocal of cosine, is secant. So we are looking for the function whose derivative is secant tangent. I say secant tangent because that's normally how it's written out. From our basic integration rules sheet, you can see that the integral of secant tangent, or tangent secant dx, is just secant of x, of course, plus c. That is because the rule for the derivative of secant is secant tangent. So we're just working backwards here. So our final answer here is secant x plus c. Now, a lot of these aren't necessarily difficult, but the challenging part is more so in the setup, or realizing how you can rewrite a quotient in certain ways. Same with quotients of trigonometric functions. All of the antiderivatives, aka the integrals that we've been finding so far, have been a general solution. We've had that plus c. When we're given an initial condition, that means that we're going to be able to actually solve for what that particular c value is. So in this first problem here, we want to find the solution of the differential equation dy dx equals 3x squared minus 1. But we're given an initial condition. We want our specific solution, or particular solution, to be the one that passes through the coordinate point 2, 4. The first thing that we're going to do is find the general solution to dy dx equals 3x squared minus 1. So to find the general solution, I multiplied both sides by dx. Then I want to take the integral of both sides. When you take the integral, in this case of 1 dy, we just get y. And taking the integral of 3x squared minus 1, we'll take the integral of each term separately using the power rule for integrating, meaning we'll have that 3 there. We'll add 1 to the 2, which we get a 3, and then that's the same value that we divide by, so that'll just be x cubed. Then here, the integral of just 1 dx is just negative x, or minus x here, because it was minus 1. Then, of course, we still have a plus c. So simplifying, we'll have y equals x cubed minus x plus c. I'm going to check that really quick by taking the derivative here and making sure that it's 3x squared minus 1. The derivative of x cubed is 3x squared. The derivative of minus x is minus 1. The derivative of a constant is nothing. So this works. This is our general solution to this differential equation. Here's a neat little picture from your textbook, and this is actually showing all of these general solutions for all the potential values of c. Of course, c does not have to be an integer, but it would just be too messy to show all the infinite values of c, but the function x cubed minus x plus whatever c value looks like this cool cubic function. We want to find the particular one that passes through 2, 4. Now it's going to be this one down here. We'll end up getting c equals negative 2 by doing some algebra. So this is, again, the general solution for any value of c. We want to find the particular value of c given this initial condition 2, 4. So let's find the particular solution. So we are given the initial condition 2, 4. So when x is 2, y is 4. So let's rewrite our general solution, y equals x cubed minus x plus c. Then we want to plug in 2 everywhere there's an x and 4 for y to solve for c. So we'll have 4 equals 2 cubed minus 2 plus c. So we'll have 4 equals 8 minus 2 plus c. 4 equals 6 plus c, and that gives us c is negative 2. Now that's not our final answer, so I don't actually need to box it. What I want to do is rewrite our general solution with our particular value of c, y equals x cubed minus x minus 2. So this is our particular solution, and this one up here with the c is our general solution. When you're given an initial condition, you're given a particular point that one of your infinite general solutions will pass through. That initial point or initial condition will allow you to find the particular value of c from your general solution to turn it from a general solution to a particular one. So our general solution is here with plus c, and our particular solution has that particular value of c. So this is the function y, such that its first derivative is 3x squared minus 1, and also we know that it passed through the point 2, 4. In this next problem, we again want to find a general solution and then also the particular solution given an initial condition. So the first thing that we want to do is take the integral, or the antiderivative, of our f prime of x. We, of course, here have the constraint that x needs to be greater than 0 because x cannot be 0. So in particular, we just want the right side of the y-axis here. So let's take a look at our f prime. So I rewrote f prime of x equals, in this case, x to the negative second rather than 1 over x squared. We are going to take the integral of both sides with respect to x. When we do that here, we'll just have f of x. And then on this side, we will have, using our power rule for integration, or the backwards power rule, if that's how you'd like to think about it, where we add 1 to our exponent, and that's the value that we divide by. Dividing by negative 1 is the same as just multiplying by negative 1, so both of those are fine. Then, of course, we need our plus c. I'm going to rewrite this a little bit nicer. So we'll have negative 1 over x and then plus c. Now, our particular solution is going to be found by using the initial condition where f of 1 equals 0. This is equivalent of getting the information that it passes through the coordinate point 1, 0. This is just saying that when x is 1, our output y is 0. So let's plug that in. We know that when x is 1, so we'll have negative 1 over 1 plus c. Our output f of x is 0. Solving for this, we'll have 0 equals negative 1 plus c, and that gives us that c has to equal 1. So our particular solution is plugging in that c value. We will have f of x equals negative 1 over x plus 1. And that's our particular solution using our initial condition. In this video, we learned how to take an antiderivative using integration techniques. And just like derivatives, integration techniques all have their own rules. Integrating and differentiating are inverses of one another. So it's basically doing the backwards thing of what you did to find the derivative. All in all, it's best to make sure that you have a reference sheet on hand while you're learning how to integrate.